at all before we get started? One thing I want to mention, and I sent an email out. We got a candidate on campus again today. 215 and 318, same extra credit rules as before for the presentation. I was going to say something else. Lost track of what I was going to say. Doesn't matter. We'll figure it out. I'm going to go over a couple of the homework problems in a second. We should also think about having our first quiz, and I think we'll do that a week from Thursday. Oh, and now we're going to say we're going to get on a few minutes early today, so we'll get out around about 10 after. So, Candace on campus, got to go to lunch, all those things. So, got a few minutes early. But next, a week from Thursday, we will do our first quiz. There you go. You're welcome. And we'll chat a little bit more about what will be covered on that on Thursday. I'll give you a new homework assignment as well on Thursday. You've got your major assignment, your first major assignment on Thursday. You'll have a new homework assignment that'll be due the following Thursday. We'll chat a little bit about what's on the test as well. And also get a little bit more insight into what your final project will be about. So, Thursday sounds like it's becoming a fun day. Actually, your next assignment we'll do, we talked about the doing Gaussian elimination with partial pivoting last time. That'll be on your next assignment. And then what we talked about today with least squares. So that's where we're headed today. All right, just a couple of things I wanted to mention with regard to the homework. By and large, went fairly well. Just a couple of little things. On the first problem, after you convert it to binary, to convert it to the machine representation, remember we need to write it in that scientific notation and do your shifted exponent. And in single precision, the shift is 127. In double precision, it would be 1023. But same idea, right? And then if you convert it to scientific notation, I believe you end up with 24 spots after the decimal place. So this last one gets chopped at the end. So that wouldn't be there. I didn't take, if you put the last one on there, I didn't take all 4, but did mention that that last one should not be there. Okay. So just be careful with that as far as the machine representation goes. If you were in double precision, that one would have stayed and you would have ended up with what? Another 29 zeros at the end? I believe that's the right number. So in any event, that was machine representation. Where is my cursor? Seriously, where's my cursor? I don't know. I guess I'll scroll with my finger. And the second one, if you're using the same standards as single precision or double precision, doesn't really matter. You're told that you can't use all zeros and all ones for the exponent. Then the only exponents that you can possibly represent are the ones from 1 through 6. Rather than 0 through 7 if we're only using 3 bits. And then if we do the shifting idea like we did with the single precision, you really can do exponents from -2 to 3. So your possible representations are, well, here's the smallest exponent I can use, and then this is the smallest manticip that we can have with all zeros. So you get 1 times 2 to the -2, which gives you a quarter. The other way, you can do 110, which gives you the 6 for the exponent, and then you can use all of the ones here, which is where that all comes from. And then you simplify that, you get 15 and 15 16ths, or 15.9375. And what else did I want to mention? The last thing I think I wanted to mention was on the divided differences. So I think a lot of you made it harder than you needed to. You can actually answer all of the questions just with one table. You don't have to make several different tables. If you do one table with all the numbers at the same time, you can just pick out the pieces that you need. So with the first 3 points, if I just use the first 3 points, I just need this little upper triangular part here, and those would be your coefficients. So you can just pick them off. You need the triangle piece that you need. So if the second part, I can't remember what the second part asked for, through the last 3, again here, The last three, you've got that little triangle part there. You just need those three numbers. One of the nice features of the table is that I can just pick out the pieces that I need. You don't have to redo them all. You do one big table and pick out the spots. So I wanted to make sure that I mentioned that. So I would not ask you to create a table this large on your quiz because you're not going to have your computer with you. However, I could envision a scenario where I give you the table and then ask you parts like this and pick out the pieces that you need. Does that make sense? Okay. So likewise, when it asks for a degree 3 through the first 4 points, again, if I just want the first 4, I could do that triangle spot right there and pick out those 4 that I need for my coefficients. So when you asked me the other day, is there an easier way to do it? Yeah, that was an easier way to do it. As far as actually computing them, no, but you can write out the pieces a little bit easier if you just have one big table to start with. Many of you had several little tables in your Excel files. So that helped. That was what I wanted to go through as far as that goes. All right. So let's continue on with kind of tying together this idea of solving systems of equations. We just touched on it a little bit. We'll go back to solving systems again later, hopefully. Again, remember my goal is to try to go through quickly a surface level of a lot of these major tech things that we do in numerical analysis, and then go back and do deeper dives into some of them. And then, of course, you can do deeper dives into other ones for your final project. That's kind of the idea. All right. So last time we just touched a little bit on solving systems of equations and how you might be able to do it a little bit more computational, a little bit better computational precision if we do things with partial pivoting. We also said that when we when we found polynomial interpolants, we also had to solve systems of equations, right? And depending on how many points or what you have, that will tell you a little bit about the complexity of the system and how much solving you have to do. And then I also mentioned this idea of a function, which I wrote down the wrong function when I started, which is why my graph looked goofy last time. This function is actually 1 over 1 plus 25x squared. I had the 25 in the wrong spot. Okay. My apologies. Again, this is referred to as the Runge function, which illustrates some issues with polynomial interpolation. So reverse engineering some things. The reverse engineering is what's showing you what some of the issues that pop up with interpolation. And this is what's going to motivate our discussion for today. So the Runge function here is in blue. Generating 5, they refer to these as nodes rather than just points. They call them nodes because we have to be fancy and call it a different name. We've got these 5 nodes that are on the Runge function. And then say, okay, well, suppose I didn't know what the function was to start with. Okay? Generated the nodes from that function, but just act like you don't know what that function was to start with. Okay? And say, I want to try to fit it with a polynomial. Okay? Well, there's 5 points. What degree polynomial will we need to use? I'm seeing fingers, but not hearing anything. 4, thank you. Good. Yeah, degree 4, right? Because I need to find a constant. I need to find a coefficient for the x squared, x cubed, x to the 4th, right? So 5 is what we would need. Does this polynomial look like it fits it particularly well? No. All right, so again, remember the whole idea of the polynomial interpolant is really what I'm trying to do is I'm trying to model the underlying function, right? It's just not enough to say, I want to find the polynomial that goes through those points. Yeah, that's what we're doing, but I want that polynomial to model relatively accurately, at the very least, the underlying function. Think about what you're typically doing. You're typically collecting data and trying to find something that models the data so that you can use that to extrapolate from that information. Right? Okay? So it's not enough that I found this function that went through those 5 points. I want to find a function that actually accurately represents what's actually going on under the hood, so to speak. Okay? So maybe, rather than just using 5 points, I use more. Was that better? Kind of yes, kind of no. Okay in the middle-ish, but bad on the ends, right? So again, and then again, now let's think about complexity of solving this. We've got 9 points. So I have to find 9 coefficients constant through the coefficient on the 8th degree term. That's a larger system to try to solve, right? Makes it uglier. Maybe I need more. How about 13 nodes? Not great on the ends, right? How about 17 nodes? Not great on the ends. I'm still not modeling the underlying function very well, particularly on the ends, right? The middle is actually pretty good because that middle looks like kind of a quartic almost, right? It's going up and it kind of bends back up again, right? So the middle's pretty good. It's those at the ends that suck, right? Because again, you're trying to model something that's very flat with a polynomial that's not flat. It's trying to use those as going through that point. If we think about this getting really, really close to the x-axis, I've got all these roots. All these roots of that polynomial are single roots, which is what a single root again means, that it crosses directly through the x-axis. It doesn't flatten out, right? So all it's doing is try to go and then it has to turn around in a hurry and come back down, and then it has to turn around in a hurry and then come back down. It has to do it relatively quickly, which is why it's super steep. Okay? So anytime you're using these equally spaced nodes on a function that's really flat, you're going to have issues with your polynomial interpolation. Okay? There are ways to help with that. There are different nodes that you can choose rather than choosing equally spaced nodes. And so that'll be a topic we come back to later. Or you can use for future investigation for a final project. One of the other, depends on what I get to. Okay. All right. So anyway, what can we do instead? Well, again, we're thinking about trying to fit this data. To make a good fit, does it necessarily actually have to force to go through each individual point? Or can it be a better fit if we just kind of made it go close to the points? Yeah, that's the idea. Okay, so that's what we're going to do today when we talk about least squares. You may have, and maybe I could even go as far as to say probably have, talked about least squares in another class, but you may not have talked about it the way that we're going to talk about it today, and it's going to be from a linear algebra perspective. The reason why I'm going to do it from a linear algebra perspective is because it's going to tie it to solving systems of equations. Okay? So let's start with relatively simple idea. Let's say I had 3 points and I wanted to fit a line through the 3 points. So let's say we start with -1, 1. I'm just making up numbers, by the way. -1, 1, 2, 5, 4, 3. Let's just plot these points super quick, just to see what I'm looking at. What did I say? Let's see. Let's go to Desmos. We had -1, 1. Oops. -1, 1. Was a 2, 5, and 4, 3. Is that what I said? It's the problem with making up points. I forget what I said. There's 3 points. Can I find a single line that goes through those 3 points? Not a trick question. Does it look like those points all lie on the same line? No. Okay. All right. So there is no way, if I'm thinking about it from a polynomial interpolation standpoint, I cannot find a degree 1 polynomial that exactly interpolates all three of those points. I have to use degree 2, right? I'm going to do that. Okay, all right. So maybe for whatever reasons, maybe I don't want to use degree 2 or a higher degree polynomial. Maybe I really want to use a line because maybe, and we'll see with a little demo that I have made up here, that maybe there's noise in the data and I'm not going to fit it directly onto it. They should have a linear relationship, whether the noise, whatever, from errors from collecting the data or the data, errors from recording the data exactly. Maybe there's little errors in there. That's what I mean by noise, right? Maybe there's little errors that don't make it fall exactly on a straight line, but we expect it to have a linear relationship. Maybe from a perspective of physics, maybe something like Hooke's law for springs, where it should be proportional to how far you stretch it, right? You would expect that to be a linear relationship, but maybe based on what instrument you're using or what the precision is for the instrument you're using to measure, maybe it's not quite linear when you collect the data. But you expect it to be linear because you know what Hooke's law says. Don't ask me too much more about physics because that's one of the things I remember, but not much past that. Okay? So, but that's what I mean by that. So you might expect it to fall in a linear relationship, but it may not be exactly for whatever reason. Okay? All right. So let's talk about what we might try to do to approximate this. So again, like I said, from a polynomial interpolation standpoint, it's impossible to find a line that's going to go through all 3 points. Okay? But it is the idea that we're going to try to start. Let's think about it from a solving systems of equations standpoint. Remember what we did when we just found our van der Waals matrix. Okay? When we did our van der Waals matrix, remember we just said plug in the point to get our matrix and then we set it equal to the right-hand side? Remember doing that? Okay. So setting that up back over here. All right. So again, we're going to fit these. Let's say we try to find one line that passes through all 3 points. We already saw from the picture that's not going to be possible, but let's just say we didn't know that it was impossible. Let's just say we tried it anyway. Okay? So one line, so our line would have the form y equals, I'll call it ax plus b. Actually, I wrote it as ax plus b. I'm going to write it the other way around, and I'm going to use Python here in a minute to define a polynomial. Using in NumPy, you can define a polynomial. When you do that, the powers are in increasing order. So that's why I'm doing it this way. Okay. It's the only reason why I flipped it around. Okay. All right. So again, what we want to do, if we want to form our van der Waals matrix to solve our system, remember again, we'll plug the data point in and we want to set it equal to the y value that's associated, right? So one equation that we would have would be b plus, I guess I should write it b minus a equals 1. Plug in -1 for x. We're supposed to get 1 out, right? We agree? What would the next equation that we would form from the 0.25? If we're using the 0.25, what's the equation that we get that we need to try to solve for a and b? Yeah. Good. B plus 2a. Good. What are you doing today? I was doing the same thing in differential equations this morning. I was writing stuff that was disappearing. B plus 2a equals 5. Cool. And the last equation? Good. B plus 4A equals 3. Good. Fantastic. Wonderful. Everybody see what those equations are coming from? We're supposed to plug in the x and get out the y. This is what I mean by we want to try to find one line that satisfies, that goes through all 3 points, right? And with all 3 points, it has to be on the line. So if I plug in the x value, I have to get out the y value, and all of these 3 have to be satisfied at the same time, so I get this system of equations, right? How many equations do we have? 3. How many variables do we have we're trying to solve for? 2, right? We refer to that as an over-determined system. That's more information than we need if there is a unique solution. That's more information than we need to find the answer. That's what over-determined is. What bad things typically happen when you have an over-determined system? You get something that is inconsistent, doesn't have a solution, right? Okay. So if we think about what this looks like from a matrix equation, we'd have the matrix, well, we'd have a 1, 1, 1 down the first column, and we'd have a negative 1, 2, 4 down the second column, right? We'd have the vector A, the other way around, BA that we're trying to solve, and on the right-hand side, I'd have the vector 1, 5, 3. That's the matrix equation that we're trying to solve, right? We agree? Yeah, cool. And again, if we think about it from a solving systems of linear equations standpoint, if I try to do my row reduction, I would augment this vector onto this matrix. I'd get a pivot here, get zeros below, right? I get a pivot here and get a 0 below. And when I did that, I'd end up with a number here that's not 0. I'm not going to go through all the work. If you go through the work, that's what you will see, right? And then when you get to that point, from solving finding an exact solution to that system of equations, you'd come up and say, has no solution, right? Whether or not you've had linear, you've done this before, I'm sure, the solving a system of equations. Okay? This pops up in lots of different contexts. But this system has no solution if you go through the row reduction or go through elimination or however you want to try to do it. All right. So finding an exact solution, we're stuck, right? We can't do it. Not possible. Not going to happen, right? But again, whatever the scenario that you're envisioning, I want to use the simplest non-constant model that I can think of to model the data. That's a line. That is the simplest model that you can come up with, right? Okay? Or I know it's supposed to follow a linear relationship, but I've got noise for however I've collected my data. But I know it's supposed to be linear. Or maybe you've just got 1,000 data points and you make a scatter plot and you can kind of see it going up like this in a linear fashion. But again, they don't all fall on one line. There's lots of different ways why you might want to say, I want a line to model this, right? Yeah, okay. So I really, really want to use a line, but I can't solve it exactly. So what do? That's the idea, all right? So let's think about this a little bit more generally. All right, so we're trying to solve the matrix equation AX equals B, where A is an M by N matrix with M greater than N, more rows than columns. I'm going to tie this as much as I can to linear. we have more rows than columns, right? So let's think about some words that you learn in linear, but let's think about it from a perspective of row reducing. If I have more rows than columns, and I try to put it in row echelon or reduced row echelon, I'm going to run out of columns before I run out of rows. So I'm not going to get a pivot in every single row, right? Which means my columns cannot span all of Rn, or my, Rm, where my column vectors are coming from. I know I'm using a lot of words that you may just be touching the surface on linear this semester, or it's been a year since you talked to me about having it in linear, okay? All right, so what do we mean by span? Span means that I can generate every single vector in my vector space by using a finite set of vectors. There's the set that generates everything. To tie it back to physics, because I know so many people in here love physics. Tie it back to physics, a lot of times you'll write vectors as something times I plus something times j plus something times k. I, j, and k are those unit vectors in the x direction, the y direction, and the z direction. And I can write everything as a linear combination of those three vectors. So that is what that means. If I can write it as a linear combination, that's what span means. Okay? Lots of words, I know. Okay, but let's tie it back to this system of equations. All right, so again, this means that we have an overdetermined system. So in general, this system will not have a solution. It can, but it may not. So how do we get around this scenario? All right. So let's start with a picture, and then we'll bring in a little bit more linear algebra, and then we'll actually solve some things. Okay. All right. So let's talk about a picture. So I just talked about the set of all linear combinations of a set of vectors is a span. Okay. Well, if I think about the set of all linear combinations of one vector, well, that just means all scalar multiples of a vector. Well, if I've got some vector and I do all scalar multiples, maybe I go out this far, maybe I go out that far, maybe I go this way, what kind of a shape do I get if I do all linear combinations of a single vector? What kind of a shape do I get? A line, right? If I do linear combinations of two vectors, just for my pictures here, if I do all linear combinations of two vectors, what kind of a shape do I get? A plane, right? Because I can go as far as I want in this direction, as far as I want in this direction, and then add them together. I get all sorts of things in the middle, right? So I get a plane. Linear combinations of three vectors, as long as they're not all on the same plane. If I do three vectors, I get space, 3 dimensions, right? And then I can get higher and higher dimensions that I can't draw. Okay, but in general, when I do all linear combinations of a set of vectors, I get some sort of, in some sense, a flat space. I know flat in 3 dimensions doesn't make a lot of sense, but I don't have a warped 3-dimensional space in 4 dimensions. So I can say flat. Okay. I don't have something that looks like a cube, but I twisted it. That's what I mean by warped, right? Or have something that's a bent cylinder or something weird, right? It's kind of flat. That's what I mean by flat. Okay. No bends. Okay. Got it. All right. My drawing sucks. B, I can't draw more than 3 dimensions on a 2-dimensional sheet. Okay. So when I do this, I'm going to think about the columns in A, and I'm going to look at all the linear combinations. I'm going to represent that with what looks like a plane here. Okay. So this plane may or may not be in 2 dimensions. This may be in 17 dimensions. I just can't draw that. Okay. This is representing all linear combinations of the columns of A. For those of you who have had linear before, what name do we give to that? That's the column space. Good. It's the column space of A. So you'd abbreviate COL of A. Okay? All right. So the idea here is that, let's go back up to what we did with our example. Trying to spend a little bit more time on this because I know either A, it's been a while, or B, you haven't done it yet for linear. Okay? All right. But let's go back over here. Notice that you probably have done this in linear. Notice that this matrix multiplication, I can write this as B times 1, 1, 1 plus A times negative 1, 2, 4. That product is a linear combination of the columns. Okay? So whenever I do this A times X that's down here in the lower left corner, whenever I do A times X, whatever the X is, that product lands in the column space. Okay? So going back to my picture, whatever I plug in here, this A times X is in my column space. So the left-hand side, when I plug something in for the X, the left-hand side 100% is in the column space. If my system is inconsistent, if my system has no solution, does that say that my B is in the column space or not in the column space? Not in the column space, all right? So my B vector points somewhere off the column space, like so. So my B is just pointing way off and out in space. It's not in that plane. Again, this is just a two-dimensional representation of something happening in 3 dimensions. This is not a most general representation that you can draw, but it's the idea of what's going on. Okay? So, again, to recap, if it's a solution, it has to be in the column space of A when I plug it in here. Okay? If it's inconsistent, that means that this is not in the column space. Does that make sense? All right. So what we're going to do instead is I want to try to make a consistent system. So here's what we're going to do to make this a consistent system. I'm going to take this and I'm going to drop it. I'm going to say the word perpendicular, but that's not the word you use for vectors. What word do you use instead? Starts with an O. It's orthogonal, right? We're doing what we're doing here is what's referred to as an orthogonal projection. It's a shadow, right? I'm dropping that vector down onto the column space of A. Okay? So what we solve instead is the system AX equals the projection of B onto the column space of A, and that's some nasty notation, I know. Okay. Think of it this way. I wish I had a yardstick with me. If the floor is my subspace or my column space of the matrix, and I've got some vector sticking out of the floor, then I would go from the tip of the vector straight down to the floor. And where that ended up is the projection. It's a shadow. Imagine the sun being right directly above it. What's the shadow that you see on the floor? Does that make sense for projection? That's what we mean by the projection. Okay? All right. All right. So that's the idea. This is what we try to solve instead. Good news is that we're not going to solve that directly, because to solve it directly, I'd have to calculate the projection and then do my row reduction and get my answer. Okay, so we're not going to do that exactly. All right. So here's what we're going to do instead, and this is where, pardon me, it requires a little bit more of the linear algebra knowledge, and then we will get into solving some things, I promise. Okay? All right. So I'm going to start with this. We did this before, where when we, actually, I guess we didn't do this. One of the methods that you have for solving systems equations, besides doing row reduction, is to take the inverse of the matrix and move it to the other side. You've done that since, I wanted to say grade school, but you probably didn't do algebra in grade school. Ever since you've started doing algebra, if I have 3x equals 9, you've multiplied both sides by the inverse. You've divided by 3, right? Multiplied by a third, okay? That's kind of the naive way to try to solve it, right? I want to divide by it, but you don't divide by matrices, you multiply by inverses. But what's one fundamental requirement for a matrix to be invertible? Not that it actually has an inverse, but even before I can even talk about inverses, what has to be true about the size of the matrix? What kind of a matrix do you have to start with? Square. And I very much don't have a square matrix here, right? Okay. So the first thing I want to do to this system is make it into a square system. And what I mean by a square system is make a square matrix on the left-hand side. Okay? That's the first thing I want to do is I want to change this system into, pardon me, into something that is square. What trick or what matrix do you think I might want to multiply on both sides so that I end up with a square matrix on the left? I don't have a lot to work with. So, sorry. Okay, I can multiply both sides by the identity, which is square, but that won't leave me with a square matrix when I'm done. Okay, remember A is m by n. What I'd really like to be at the end is end up with an n by n. Say it again. Yeah, I want to multiply by some n by m matrix, right? Yeah, fantastic. That's exactly right. If I multiply by the A transpose, then A transpose A is n by n. That's exactly what we want to do. I want to multiply by the transpose. So remember, the transpose reverses, flip-flops columns and rows. That's what the transpose does. Okay? Flip-flops your rows and columns. So just to use this with numbers, our A originally was, what was it? It was 1, 1, 1, negative 1, 2, 4. Is that what we had to start with? Is that right? Okay. So your A transpose then would be the other way. It would be 1, 1, 1, negative 1, 2, 4. I take the first column, make it the first row. Take the second column, make it the second row. That look familiar? I hope. If not, that's how you do it. Okay. All right. So we're going to knock both sides with an A transpose. Now, it turns out that as long as, this is a theorem, we're not going to do the theorem. It turns out that as long as A has linearly independent columns, then A transpose A has an inverse. It's actually if and only if. So as long as you have linearly independent columns, then you have an inverse. This A transpose A will have an inverse. Okay? All right. So this tells us how we're going to solve it, but let's talk about why it is a solution for just briefly. And I know this is going to bring back Some PTSD for people that had me. But and you may not have seen it in linear if you're in there now. Okay. But here's the idea. What I'm going to just do a little bit here. I'm going to move this to the other side. And I'm going to factor out the A transpose. Okay. Did I do that right? No. Anyway. Anyway, that's what that looks like, right? I think I'm doing this right. No, whatever. I'm going to talk around it if I'm not doing it right because I know what this is supposed to be. All right. I'm taking A transpose, I'm multiplying it by some vector, and I get 0. There's another matrix, or there's another space associated with a matrix that this is representative of. When I take if I take a vector and I hit it with the matrix and I get 0, that vector lives in something space. You remember what the word is? We had row space, we had column space, and we had null space. It's in the null space of the matrix. Okay? So this A minus BX, excuse me, try that again, AX minus B, this lives in, is in what we refer to the null space of A transpose. Null space is just the set of every vector so that when you hit it with the matrix, you get 0. That's what null space is. If you multiply it by the matrix, you get 0. That's what null space is. Okay. If you do it from a solving system of equations idea, it's the solution set of AX equals 0. It's the set of solutions to the homogeneous system. Okay. That's all null space means. It's just a fancy word. Okay. But there's another fanciness of this. There's the concept of orthogonal complement. I know that's been a long time. This is the orthogonal complement of the column space of A. To give you an idea of what we mean by, I know it's a lot of words, and it's okay. Okay, I'm not going to expect you to remember all the words. Okay. Orthogonal complement is not that bad of an idea. So the easiest way to think about it, let's draw a couple of pictures here on the board. Here's just the XY plane. Okay. If you were to guess, just to guess, and I have to have a fundamental understanding of what's going on. If I ask you to guess what the orthogonal complement of the x-axis is, what do you think it is? It's the y-axis, yeah. So what's the idea here? Well, again, if I think about it, I can write everything in the xy plane as something times the x-coordinate plus something times the y-coordinate, right? It's that linear independence idea, right? Orthogonal means they're perpendicular. In geometry terms, it means they're perpendicular to each other. Complement means it fills up the rest of the overarching space. Okay? So, if I do this in 3 dimensions, where I have an x, a y, and a z, if I want the orthogonal complement to the xy plane, what do you think is the orthogonal complement to that 2 dimensions? Z, the 3rd dimension, right? If I asked you what's the orthogonal complement to the 1-dimensional x-axis, what do you think that would be? If I want the orthogonal, so perpendicular, everything that's perpendicular to just the x-axis, what would that be? Yeah, all the YZ plane, the whole thing, right? X-axis takes up one dimension, and its complement has to take up the other two. And I can not bend, but I can rotate, shift the. I can't shift them; they have to go through the origin, but I can rotate things around, right? So if I had like, say, this was my subspace, that would be its orthogonal complement. That makes sense. Okay, that's orthogonal complement. Why do I care? All right. So let's go back to my picture. I'm just going to redraw it down here. AX has to live down here. B is up here. I want AX to equal the projection, right? From a vector standpoint, if this is my projection, I'm going to call it a W just to have to keep having the right column space of A in there again. Can you tell me what this vector has to be? If this is my B, and this is the name I'm giving to this one, can you tell me how to find that vector? This is just vectors. How do you find that vector that goes from tip to tip? I got physics kids in here. Come on. You know this one. Let's do this. Let me draw it off to the side. If I have this vector U and this vector V, and I want that vector that way, what do you do to U and V? It's not quite add. It's the other one. It says rectum, right? Right? This has to look somewhat familiar. I know many of you had Calc 3 and would have done that in Calc 3 as well. Do it in physics, right? Okay, let's do this off to the side since we're all looking at me like I'm nuts. All right, you've certainly seen parallelogram law, right? Oops. You got to make noises when you draw it. You've done that, yes? You've done that one, right? Okay. Well, why is the other one the way it is? Well, if I do, start with this. What's that? That's negative U, right? And so now do the same thing. Make your parallelogram. What's that? That's V minus U, isn't it? And then that's the same length as that is over there. Okay. Shoo. All right. Back over here. This is, either way, it doesn't matter which direction you go. I'm going to write it as B minus AX. It doesn't matter. Or B minus the projection of B onto W. That subtraction there is what we need. Okay? So all of that said, this piece is in the null space, which is in the orthogonal complement. So it's this piece here, right? So working backwards now, this is the thing that I need. That's the projection. All right? So going backwards, that's what we need. So if we go back up to working our way backward, this gets us to that. Okay? This has a special name. The A transpose AX equals A transpose B. It's called the normal equations. I know it is called the normal equation. Sounds odd. But as long as the thing on the left is invertible, now I can just solve it. I can take the inverse to the other side and be done. So if A transpose A inverse exists, then the least squares solution is X equals A transpose A inverse times A transpose times B. That's how we find it. Okay. I know that was a long way to get there, but I didn't want to just write it down and tell you what it was. Okay. There really is some honest to goodness least squares stuff going on. Why do we call it least squares? Well, if you did any other projection down to this space that's not straight down, what would the length of this vector be relative to that one? If I don't go in a perpendicular direction, what's going to happen to the length of my vector? Is it going to get bigger or smaller? Bigger, right? If I fall straight to the floor, or if I go from here down to the floor, which is longer? That way, right? Right? So that's why it's least, because that's the smallest direction. It's least squares because what are we minimizing? We're minimizing magnitude. And usually if you want to do things from a calculus perspective and doing things with distance, you'll square it to get rid of the square root. So you minimize the squares. So that's why it's called least squares. That's where the name comes from. It's a minimizing idea. You can actually do all of this from a calculus perspective, by the way. But that's not what we're talking about right now in this class. We're talking about doing systems of equations. So that's why we approach it this way. All right. Now you've had all that fun. Let's see if we can see why we care. All right. So let's pull up a demo here. You don't have to go along with this. You can just watch. That's okay. There's my mouse. All right. I did not log in because, of course, I did not log in. Why would I log in? Leave. Let's cancel because I need to switch accounts. And drive. Least squares. All right. So I'll show you where this comes from here in a second. So what I've done is, oh, that could have been deleted anyway. What I've done is I'm creating some data, as soon as it loads, creating some data that should be fit by a cubic third degree polynomial, but introducing some noise. So let me tell you what I've did here. Created here some random x's and some random y's. They're not all that random. I'm going from -5 to 5 as kind of base points, but I'm just tweaking them slightly with a random piece here. Letting it go a little bit left or a little bit right, depending on what it picks. This function picks a random decimal between 0 and 1. So subtracting it half just to give me something between -1/2 and 1/2. Okay. And then making sure I don't go into the next interval, I cut that interval in half and then just add what I have for the x value. So I'm just picking some random-ish x values, and then I'm plugging those into a cubic polynomial that I just started with. I just made it up. But again, introducing some random noise here that puts some vertical noise in. Okay? All right. Does that make sense what I did? Okay. When I did that, that's kind of the picture. You can kind of see the cubic nature, but it's not exactly a cubic, right? Okay. And then again, if I hit it again, I get a different set of points. Slightly different, but it'll still have that cubic shape. That's why I did it this way. Okay. All right. So again, I want to try to fit this with a cubic. Well, notice here I've got, 11 points? So I'd have 11 equations. If I want to fit this with a cubic, I would have 4 unknowns. Right? I need a constant an x squared, and an x cubed. 4 unknowns, but I have 11 equations and 4 unknowns. That's definitely overdetermined, right? Now let's see why I might want to fit this with a cubic rather than fit it with an 11th degree polynomial. Because that's what we've done before, right? Polynomial interpolation. Well, that's what the first one is here. You can see the old output. That's not going to do the same thing. So what did I do in this code? I set up the Vandermonde matrix, right? Notice here, and I'm going to tell you what this function was in NumPy. Remember again, if I want to start with the constants, then the x's, and the x squared, we have that extra parameter in the Vandermonde matrix of setting increasing equal to true. Okay. I used the linear algebra packages to solve the system there, right? And then once I got these coefficients, once I solved try that again. Once I solved the system, I get the coefficients I want, right, for the polynomial. Once I have the coefficients, I can define a polynomial in NumPy using the polynomial.polynomial function. Why it's twice, I don't know. Well, I do know. They have a whole package of things. This is the thing that creates the polynomial. I know why it's two. It just looks weird. Okay. Once I do that, then I can evaluate the polynomial at different points. So created 100 points between -5 to 5, made the associated y values, and then just plotted it to get the curve. That's what that looks like. And I don't know if I hit it or not. I'll just hit it again because it doesn't matter. There's what the 11th degree polynomial looks like. Does that look like a good fit to the data that we just came up with? Not really. And again, why not? Why is it not a good fit for the data? Well, A, I created the data from some underlying cubic, so duh, an 11th degree polynomial is probably not the best. But what are we forcing when we do interpolation? What's being forced? What do we have to do with the curve? What does it have to do? It has to go through every point, right? We're forcing it to go through every point, which over here and over here is making a lot of wild turns, right? To be able to force it to go through, which is not what we want to do necessarily. Okay? So what do we do instead? All right. So just to show you a couple of other functions in here, I created NumPy arrays out of the x's and y's that created because I'm going to do a bunch of NumPy functions. Some NumPy functions will take lists as inputs and some don't. So if I convert them over to arrays, then I don't have to worry about it. NumPy is a little bit quirky in that way. Okay. All right, so here I just created a column of ones just so that I would have what I need. So remember, I'm setting up my system of equations now. I'm trying to set up the system of equations AX equals B. Okay? I can't use the Vandermonde matrix because the Vandermonde matrix is square, right? So I'm just creating the matrix that I need. The first column I had the ones in because that was the constant term. Then the other ones were x's, x squareds, and x cubes. Right? So that's all I'm doing there is just making a matrix. Trying to make a matrix. That's what this column stack does here, right? So now I've got a NumPy vector of all ones, a NumPy vector of the x's, the x squareds, the x cubes. I want those to be columns, so I use the column stack command to be able to do it. And people in here familiar with those or not? I don't want to bore you if you already know how to do that. Does this look new or does it look new? Good, then I'm telling you something new. Yay! Okay. All right. So that's what the column stack does. So if you start with vectors that you want as columns, make sure they're arrays because column stack will not take a list. It'll take a list, but it has to be a list of arrays. Okay. So make them arrays, make a list of arrays in the order that you want, and then it'll stack them. Okay. There's also an hstack command, but that requires a little bit more work because what hstack does is it puts them all in one big long vector, and then you have to do what's called reshaping the matrix. This seems easier because I want to put them in columns, so why wouldn't I just stack the columns? Okay. All right. So this is just creating that matrix A that we had. I solved the system. So notice how I solved it. I took the inverse of A transpose A. So let's talk about the syntax here. If I have a matrix, which I do here, a numpy array is just considered as a matrix if it's in the dimensions that we need. Dot T does the transpose, has to be a capital T. Matrix multiplication is done with the at symbol. So this is A transpose times A, and this takes the inverse. It's in the linear algebra package. Okay. All right. And then we multiply by A transpose times the B vector, which I have as my Y value. Okay? Is that okay? All right. Once I found, that's really basically my projection, if you will, that's why I called it that. But I'm going to create the polynomial with those as my coefficients. Okay? And then I'm just going to plot it and see what it looks like. There you go. That's a much better fit. And then you can also talk about how good of a fit that is, but that's good. I will do that on Thursday, but talk a little bit about how good the fit is. Is that okay? Let's see if we can do that with the line that we just came up with. Let's see if we can do that for the 3 points. Let's see if we can put it together. Okay. All right. So let me just start a new notebook. By the way, I will post this on Moodle so you can get it, so you can see the code. Okay. So let's see if we can open a new notebook. No, I want to just create a new notebook. Try again. New notebook. All right. Oops. All right, so all I'm doing there is importing NumPy, importing the PyPlot package out of Matplotlib, and importing the linear algebra package. All right. Okay, so let's first just get a scatter plot of those 3 points that we did. Okay, so the x's were, what were they? They were -1, 2, and 4. Is that what I did? Is that right? And the y's were 1, 5, and 3. Okay. All right. So all I want to do here is get a scatter plot of those points as x's comma y's. So my lists have the same length. All right, let's see if I did that correctly. Live coding is always fun. Okay, there they are. Hey, there's my 3 points. Yay. All right. So let's solve our system. So let's create our system. This one's a little bit easier since we just have a few points to do. All right. A couple of ways we can do this, but let's do it kind of this a little bit simpler way. I'm going to create an array that makes my matrix. I can make a matrix by put it basically with list of lists. Yeah. Oh, sure. Yep. So I can do a matrix as a list of lists by row. Okay. So the first row was what? 1, -1. The second row was 1, 2. and the third row was 1, 4. Is that right? Okay. And I'll just write it B this time. Oops. Our B was what? -1, 5, and 3. That was our Y values. Was it positive? Oh, it was +1. Thank you. Okay. And then I just use the solution to my normal equations. So my coefficients will be, pardon me. The coefficients will be that inverse of A transpose times A, right? Basically, we're dividing by that product. That's matrix inverse, right? Multiplied by A transpose multiplied by B. That's the syntax. Let me get spaces in there so you can see it a little bit better. What's that? You're just chatting.
No, it was relevant, but
oh,
we got it.
Okay. All right. By the way, you could also do it using the solve command because you're trying to solve the system. A transpose A equals A transpose B, or yeah, A transpose A X equals A transpose B. So you can also use the solve command in the linear, right? Okay. So there's a couple of ways to get at it. Those are the coefficients for my polynomial. So I'll call it P equals, that command was np polynomial dot polynomial of the coefficients, right? Let's just print the P so you can see what it looks like, and then we'll come back and do the rest of this. It really does use those, okay? So if you got the solution to the system, you would get 2.2105 whatever, and then a 0.47368 whatever. That would be the solution to that. Okay. But you can see how it formats it for the polynomial. It's kind of nice. Again, it's an increasing fashion. That was why I made sure I put it in the order that I did. Constants, then x's, then x squared, and so on up the line. All right. So let's see if we can plot this real quick. Oops. The linspace command in NumPy creates a certain number of points between two values that you give it. Okay. So in this case, we'll just go from -1 to, get out of my way, 4. Where did it go? There it is. And we'll create I just usually use 100 points. Just try to make it enough points to make it look smooth. The y values will just be the polynomial evaluated at the x values. Have you done this part before with doing Matplotlib? No? It's okay. We're doing it now. All right. So then we'll do, let's do put the scatter plot in there again. Actually, what I'll do that's fine. I'll put the scatter in there again. And then not hit the enter key too soon. Then I'll also do plotting the x values and the y values. And then show. So the scatter command just puts the points. The plot command will kind of do the connect the dots with the points. And that's why I wanted to make sure I put enough points in my x's so they get something that looks smooth. Okay. This should work. And there you get the least squares line. Oh, by the way, of course, least squares packages are built into Python, so you can just do it that way too. But where's the fun in that? This tells you where the things come from. Okay. Is that right? So to give you an idea of something that you might look at for your final project, we're doing what's called linear least squares. There are also methods that you could do non-linear least squares, which talk about solving different types of systems and doing approximations that way. So that would be something that you could investigate for a final project. We'll talk a little bit more about that next time as well. So next time we got a lot of things to do, right? Give you your homework, talk a little bit about what your quiz is going to look like, talk about a little bit more about what your final project looks like, and then we'll also talk about how we can talk about how good these models are that we're doing. All right? We're going to get out a few minutes early because, like I said, the lunch with the candidate today. So we're all good for the day. Have a good one. We will see you on Thursday.